Yeah, so I guess go ahead.
We're ready to go? Yeah. This code doesn't compile. In this situation, to propagate the value of the unique putter, we need to move for correctness. This code, on the other hand, does compile. We don't need to move vector for correctness, but we can move it for efficiency. Ref qualification, of course, isn't just important. Here, we can also apply it to, for example, invoking an invocable. But of course, no one would write this code anymore since C++23 has shipped. Nonetheless, as we move into the asynchronous domain and we get the asynchronous analog of a synchronous function, this analysis also applies. It applies in the form of something I described in my talk yesterday as shottedness, whether or not you need to connect a sender as an R value or an L value. In yesterday's talk, we implemented when all range, and so I presented shottedness in terms of the properties of the wrapped range. If the range can only be traversed once because it is no stronger than input, of course, the operation can only be started one time because iterating over the range is consumptive thereof. On the other hand, for forward or stronger ranges, of course, we can traverse them multiple times, and so those senders are L-value connectable. But that's just about correctness. What about moving for efficiency? Are there situations where R-value connecting a multishot when all range sender can unlock additional efficiency? Are there situations in which we can determine a range owns its elements and move therefrom? The first thing we're going to try and look at, the simplest, is say, well, if the range is an R value, we'll apply as R value to it. After all, we have itermove as a customization point, so all those non-owning ranges can just opt out. We're going to write forward range, which helps us, which has a constrained version on an R value reference and applies R value as R value thereto. But unfortunately, stood span doesn't customize itermove, and so if you use this with stood span, it rips the guts out of all the elements, and so that's clearly not workable. Maybe we can try and work around this by looking instead to the borrowedness of the range. After all, span is borrowed, and we say that non-borrowed ranges are the only ones that we apply this optimization to. Now we go back and we reformulate forward range so that we just get the forwarding behavior for borrowed ranges, and we wrap everything else in as R value. But I've learned at this conference that people actually write shared view. Shared view is not borrowed, but we also can't steal its elements because having the shared view doesn't mean we have unique ownership of those elements. And so this is not workable either. But maybe we can fall back on the range view divide. We can say that if a range is not a view, then it owns its elements. And if a range is a view, then it owns its elements if it's move only. After all, if it was copyable, the copy would be big O of 1, and therefore it probably doesn't own it. If it's copyable, the copy would be big O1, therefore it probably doesn't own its elements. And so we can write some code that looks slightly more complicated to model this, but then we turn around and we say, wait a second, isn't stood optional copyable and a view? And if this surprises you, it's pretty late breaking information, but it's true. And so I'm going to say we can't do that either and just give up completely. We're going to have code that looks like this, which doesn't compile for no reason. I own that vector. It's in a when all range sender. The when all range sender is being connected as an R value, but we can't possibly glean information about whether or not we can steal the contents from this range. We instead need to manually communicate information the type system already has by adding as R value ourselves. It's unfortunate, but maybe this is just the way ranges work. For now, unfortunately, I'm limited by the technology of my time.